Hello students. In this video, we will review the writing of Lewis structures of some common molecules and molecular ions. And I will also introduce you to the concept of resonance. This video might also be relevant to SL students who want to review the writing of Lewis structures of common molecules and molecular ions, except the idea of resonance. Students, instead of putting together one slide in which I had all the steps written, I decided to write one step at a time for the molecules and then apply the same steps to the subsequent cases. So I hope that works for all. So in this case, we have a simple molecule, which is ozone, O3. So step number one is to count the total number of electrons. Now, when we talk about the total number of electrons, we are talking about the valence electrons of all the atoms that are there in the molecule or the molecular ion. So in this case, it's all the three oxygen atoms. And if it's a molecular ion, then we have to account for its charge as well. What I mean is that if it's a positive ion, then that charge has to be subtracted from the total number of electrons that we get from here. And if it's a negative ion, then we have to add that charge to the total number of valence electrons that we get here. We'll come across some examples which deal with this. But right now we have a neutral entity which is ozone, and it has three oxygen atoms. We know that each oxygen has 6 electrons in its valence shell, which means 3 oxygen are going to have 18 electrons in the total in the total molecule. So this means that our final Lewis structure should account for these 18 electrons. That's going to be a check for us. In the second step, we place the central and peripheral atoms and join them by single bonds. So in this case, all our atoms are oxygen, so it really doesn't make a difference what we place at the center and or at the periphery. So we have three oxygen atoms. Let's just line them up like this. And we have a single bond which we connect them with. So we know that a single bond accounts for 2 electrons. So we had to account for 18 electrons, right? And each of these single bonds accounts for 2 electrons. So that means out of the 18, now we need to only account for 14 more electrons in the subsequent steps. Now let me redraw the structure that we got in the previous slide, right? And according to the previous slide, we need to account for 14 more electrons. Now what we do here is that we complete the valence shell of the peripheral atoms. So we complete the valence shell of the peripheral atoms by putting those electrons as lone pairs. So we have 3 lone pairs on each oxygen at the periphery. So from the previous slide, we had to account for 14 more electrons, and now since we have a total of 6 lone pairs on the peripheral atoms, that means out of these 14 electrons, 12 have already been accounted. So that means we only need to account for 2 more electrons in the next step. So let me redraw what I did in the previous slide. So now we have just 2 more electrons to accommodate. So if there are any electrons remaining, we put them as a lone pair on the central atom. So we go ahead and put that as a lone pair on the central atom. But still this Lewis structure is incomplete because as we can see clearly, the central atom, the central oxygen over here does not really have a complete octet. If we count the total number of electrons here, that comes out to be 6. So what do we do then? I'll just redraw the structure from the previous case. All right. So now if the central atom's octet is still not complete, and here we are not talking about those molecules which have expanded octet, then what we need to do is we need to convert one of the lone pair of electrons of the peripheral atom to make a bond with the central atom. So that means we can use either of these two oxygens lone pair, just one lone pair, and convert them into a bond. So let's just do with this one. So what we'll do is we'll use this to make a covalent bond here. And when we do that, the final structure looks like this, right? Now, you might argue that the same could have been done with the other oxygen as well. So rather than this oxygen over here, I could have used the lone pair from this oxygen as well, and that is quite true. So the other structure that we could have had was this. Now, when we look at both of these structures, we have now accounted for all the 18 electrons and the octet of the central and as well as the peripheral atoms are complete. So, this is the Lewis structure of an ozone molecule. But here's the catch. Now, since ozone can be depicted by both of the structures, we see here that there is a disparity in the bond length of the single and the double bond. We can see here that the single bond is just longer than the double bond, and that's quite obvious because there is greater electrostatic attraction between the nuclei and the shared electrons in a double bond as compared to a single bond. But as you might have figured out in the engage section of this inquiry board, the actual bond length lies somewhere between the single and the double bond. And this is where we invoke the concept of resonance. Now, before I explain the concept of resonance, let me introduce you to two terms which will be explained in more detail towards the end of the unit, which is the concept of sigma bond and a pi bond. So the first bond that's formed between any two atoms, and I'm talking of covalent bond here, is a sigma bond. So when we refer to a just a single bond between two atoms, that is a sigma bond. Now, how exactly is a sigma bond formed and what makes it distinct? That's something that we will discuss towards the end of the unit. Any bond that is formed between two atoms after the formation of sigma bond is a pi bond. So as we can see in these two examples, here we have a double bond. So let's say the first bond formed here, this was a sigma bond. The other is designated as a pi bond. All right, and the same applies here. So the first bond formed is a sigma bond and the second is a pi bond. Of course, by looking at the structure, it's both of these bonds actually seem alike, but that's not exactly the case. So if you could just wait for towards the end of the unit to understand the difference between a sigma and a pi bond, but for now it would be enough for you to understand that the first bond that is formed between two atoms is a sigma bond, and the second or the third bond which is formed between the same two atoms would be called a pi bond. So in a sense, what is happening in resonance is that the pi bond is not localized. That means the pi bond is not restricted to between two specific atoms in a molecule. Rather, in this depiction, as you can see, the pi bond is delocalized or spread over the entire molecule. This phenomenon of pi electron delocalization is what is called resonance. Now, due to resonance, the molecule gets a lot more stability. Now, you might ask how. That's because instead of the electron density being concentrated in one region, it's being spread over the entire molecule, which actually decreases the reactivity and enhances the stability of the molecule. Okay, so this is basically the real structure of ozone. But as you can clearly see, this is not a Lewis structure. So the actual structure of a molecule, of the molecule that has resonance going on, is called a resonance hybrid. And this structure cannot be represented by a Lewis structure because a Lewis structure cannot represent a partial bond, right? So you might be thinking, is ozone this molecule, or this molecule? So it is actually the third molecule, but the third molecule, that is the resonance hybrid, is basically formed as a result of these two resonating structures. Resonating structures are generally written separated by a double-headed arrow. Please do understand that this does not mean that ozone is oscillating between these two structures. None of these two structures actually depict the reality of ozone. What ozone is actually is the third form where the pi electrons are actually spread over the entire molecule. And this results in the bond being shorter than a single bond but longer than a double bond. Let's understand this with a few more examples. So our next example is how to write the Lewis structure of nitrite ion. Okay, so again, step number one is to count the total number of electrons. So we have nitrogen, which has 5 electrons, and then we have two oxygen. Each of those oxygen has 6 valence electrons. And then, because this is not a neutral entity, this is a charged entity, so we add the charge. All right. So the total number of electron amounts to 5 plus 12 plus 1. That means 18 electrons. So our overall Lewis structure needs to account for these many electrons. So again, following the second step, we place the central atom and peripheral atoms and we join them by single bonds. So we have nitrogen as the central atom, we have the two oxygens as the peripheral atom, and we join them by a single bond. So again, just as in the example before, a single bond accounts for total of 2 electrons. We have two single bonds. So that means out of the 18 electrons that we need to account for, 4 have already been taken care of, which means we only need to account for 14 more electrons. Let me write the structure that we deduced in the previous slide. Okay, and we have 14 more electrons left to account for. So here, just as before, we complete the valence shell of the peripheral atoms by having lone pairs. So we have 3 lone pairs here, and we have 3 lone pairs here. So that makes up 6 lone pairs. So 6 lone pairs imply 12 electrons, which means 12 electrons have now been accounted for, and we are now left with just 2 more electrons. So just as discussed in the previous example, we have the central atom, the peripheral atom. The peripheral atom has the lone pairs in place, and we needed to just account for 2 more electrons, and as discussed in the previous example, we put those 2 electrons as a lone pair. Okay, but again, just like in the previous example, we can see that the octet of nitrogen is not complete. So you might be able to guess where this is going in the next slide. So this is what we had in the previous slide. All right. Now, since the central atom's octet is not complete, what we do is we take any of those two peripheral atoms and use their electrons to make the second bond. So let's choose this one, right? Now, if we do that, we will have right? And because there is a overall negative charge, so we put a square bracket and we put a negative charge, right? So now the octets of all the atoms are satisfied, and and we have the overall number of electrons also satisfied. But just as discussed in the previous example, this could also have been achieved using electrons from the other oxygen atom. So in that case, the structure would have been written like this, the negative charge, right? So both of these look quite equivalent. It's kind of like just swapping the double bond with from one atom to another atom. But again, we can see that where this is leading us to in the context of resonance. So these two in reality are the resonating structures of nitrite ion, which means that this is not the real nitrite ion, because what would happen in reality is that the pi bond, that's the second bond that's being formed between the nitrogen and oxygen atom, that would get delocalized, and we represent that using dotted lines, right? So again, resonance is involved in this molecular ion, which leads to a partial double bond character. Resonance is nothing but pi electron delocalization, which leads to more stability, as the electron, instead of concentrated between any two atoms, is spread over a larger area. Let's take another example. Let's take the case of carbonate ion. Now, if you are fairly confident of writing this on your own, please pause this video and try to attempt this on your own. Alright, so this has a carbon atom which has four valence electrons. It has three oxygen atoms, each of which has six valence electrons, and we have an overall charge of -2, which means these two electrons have to be added on. So if we add this together, we have 4 plus 18 plus 2, so that amounts to 24 electrons, which means our resultant resonating structures should have 24 electrons in them. So just as before, we're going to place the central atom, and then we're going to place the peripheral atoms around the central atoms, right? And remember, we had to account for 24 electrons. So we make a single bond with all the three peripheral oxygens, and each single bond accounts for two electrons. So that means six electrons have already been accounted for. So that just leaves 18 electrons more. So let's just draw the structure that we were able to deduce in the previous slide, and we had to account for 18 more electrons. So again, what we do is we complete the valence shell of the peripheral atom by placing the lone pairs appropriately. So there are three lone pairs which we can put, yeah, and so we have a total of nine lone pairs over here. So that would mean all the remaining 18 electrons have been accounted for, and in reality, then therefore this should be a perfect Lewis structure, since there are no electrons remaining. But if I draw the structure that we deduced, there is an issue. So let me just draw the structure that we deduced before, and I think you kind of understand where we are heading to. So the central atom, so even though we have accommodated the total number of 24 electrons, the central atom, which is carbon, its octet is not complete. So we'll use the same strategy. We basically uh, have one of the lone pairs go to the central atom, making a bond with the central atom. So we'll do that. We'll do that. So we have these three oxygens. We had their lone pairs, right? And so we use one of them to make a bond with the central atom. So if this one makes the bond, this becomes C, and then we have three lone pairs here, three lone pairs here, and if there is a double bond here, and then two lone pairs here, if this is the oxygen that donates. Now, instead of this oxygen, if this oxygen, this other one donates, then how would this look like? In this case, it's going to look like oxygen here with two lone pairs making a double bond with the central carbon, and the other two oxygens, they have their usual three lone pair of electrons. So this is also a possible structure. Another possible structure is if the top oxygen actually donates one of its lone pair, right? So we have carbon, we have a double bond, and this has just two lone pairs, and the other, well, they have their three lone pairs. Okay, so all of these structures, as you can see, they are virtually identical structures, but each of them actually uses a different oxygen, peripheral oxygen atom to make the second bond with the central carbon atom. But these are our Lewis structures. These three structures that we deduced are our Lewis structures. Um, but as you can see where it's heading, none of them are actually depicting the real molecular ion, which is carbonate ion. So these are the three resonating structures that we deduced in our previous slide. So you might just pause this video here and think, how would the real carbonate ion actually look like? Okay, so the real carbonate ion would have our three oxygens and carbon at the center, but the bonds are going to be partial bonds because of pi electron delocalization. Notice that I'm not putting any lone pairs because this is not a Lewis structure. All right, so I hope this tutorial was helpful in for you to understand how to draw Lewis structures of simple molecules and molecular ions, and for the HL students also the basic concept of resonance, which is just pi electron delocalization, which helps in granting stability to certain species. Thank you for watching.